Manhood is patience. Mastery is 9 times patience. Ursula K. Le Guin, a wizard of Earthsea. Hello everyone, this is the last section of this course, putting it all together. In this section, we'll apply ideas from all the previous sections to see what a complete working Puppet infrastructure looks like, using a demonstration repo which illustrates all the principles explained in this course. You can use it as the basis of your own Puppet codebase, adapting and expanding it as needed. Now we move on to the first video of this section, getting the demo repo. In this video, we'll see copying the repo, understanding it, and the Bootstrap process. The demo repo is available on Github, and you can clone it in the same way as for the example repo for this course by running this command. It contains everything you'll need to manage nodes with Puppet. It also includes a Vagrant file, so you can try out the repo on a Vagrant virtual machine. Now, if we are going to use the demo repo as the basis for your own Puppet repo, you need to make a copy of it so that you can edit and maintain it yourself. You can do this in 2 ways. One is to fork the repo to your own GitHub account. To do this, log into GitHub and browse to the demo repo URL. Look for the Fork button at the top right of the page and click it. This will create a new repo under your account that will contain all the code and history from the demo repo. Alternatively, you can do this. Create a new repo in your GitHub account. Name it control-repo or whatever you prefer. Make a note of the repo URL. Clone the demo repo to your personal machine. Rename the original repository remote so you can get updates in future. Add your new repo as the origin remote using the URL for your repo you noted earlier. Push to the new remote. Your repo now contains a complete copy of the demo repo, which you can edit and customize just as you like. As the original repo is updated in the future, you will be able to pull these changes into your own version. To get changes from upstream, run these commands. It's now time to see how all the ideas from the previous sections fit together. It should be helpful for you to see how a complete Puppet infrastructure works, and you can also use this repo as a basis for your own projects. We start with control repo. A control repo is a Puppet codebase which contains no modules or only site-specific modules, and it's a good way to organize your Puppet code. Our Puppet repo needs to contain only a Puppet file, along with our hire data and the role and profile modules. Because R10K expects to manage everything in the modules directory using the Puppet file, our site-specific modules are kept in a separate directory in the control repo named Site Modules. To enable this, we need to add this setting to the environment.conf file. This adds site modules to the list of places Puppet will look for modules. We will be using R10K and a Puppet file to manage all third-party modules. Accordingly, there is no modules directory in the demo repo. Here's the Puppet file with the list of modules we need for the initial repo. Of course, as you adapt the repo to your own needs, you'll be adding more modules to this list. We'll see later how these modules are used. Every so often, use the Generate Puppet File tool to automatically update your module versions and dependencies. Copy and paste the output back into your Puppet file, replacing the existing mod statements. Now, as you may recall from Section 3, Classes, Roles and Profiles, we use hire data to determine which classes and resources should be applied to the node. The common classes are listed in common.yaml. and there is a pre-node data file for the demo node which includes the role demo class. These classes are included by this line in manifest site.pp. Role classes identify by name what the function of the node is and define what profile classes should be included. It's common practice to keep your role classes in a role module, and as this is a site-specific module, it's filed under Site Modules. Here's the role demo role manifest. Moving on to profiles. A profile class identifies by name some specific piece of software or functionality required for a role and declares the necessary resources to manage it. Often, there are profiles which are common to all nodes, our user account for example, and a few others. It's logical to keep these in the common.yaml hierodata file so that these profiles will be included by all nodes. Here are the classes included in common.yaml. In the hierodata, classes are listed in alphabetical order. This can be helpful when you have many classes included and can make it easier to see whether or not a given class is already in the list. Let's see users and access control now. The Puppet Labs Accounts module provides a standard way to handle user accounts with the Accounts user class. Accordingly, we will use this to manage our users in the Profile Users class. You could just list the required users as literal resources in your Puppet manifest, of course. But instead, let's take the data-driven approach described in Section 1, Managing Data with Hiera, and define our users with hierodata. This is what the data structure looks like. Here's the code in the user's profile to read the data and create the corresponding accounts user resources. As you can see, we fetch all the user data into a single user's hash with a call to lookup. We iterate over the hash, declaring an accounts user resource for each user, whose attributes are loaded from the hash data. Note that when using the accounts user resource, the SSH keys attribute must contain an array of authorized SSH public keys for the user. Let's focus on SSH configuration. It's good security practice to restrict SSH logins to a set of named users, using the Allow Users directive in etc ssh sshhd config. Here's the template for the sshd config file. We declare that the template takes an Allow Users parameter, which is an array of string values. Because the Allow Users parameter in sshd config expects a space-separated list of users, we call the join function from the standard library to create this list from the Puppet array. Here's the relevant hierodata. We could have just constructed the list from the user's hash, which contains all known users, but we don't necessarily want everyone on the list to be able to log into every node. Conversely, we may need to allow logins for some accounts which are not managed by Puppet. An example is the Ubuntu account, which is required by Vagrant in order to manage the VM properly. If you're not using Vagrant boxes, you can remove the Ubuntu user from the list. The code to read this hierodata and populate the template is like this. This is a package file service pattern. First, we install the OpenSSH server package. This is usually already installed, but it's good style to declare the package anyway. Next, we manage the etc ssh sshd config file with a template, which we populate using hierodata from a call to lookup allow users array string unique. This file notifies the SSH service whenever it changes. Finally, we declare the SSH service and specify that it should be running and enabled at boot time. Take a look at Sudoers Configuration now. The sudo command is the standard Unix mechanism for controlling user privileges. It's usually used to allow normal users to run commands with the privileges of the root user. Sudo also audits and records which user ran which commands. You can also specify very fine-grained permissions, such as allowing a user to run only a certain command as root, but no others. The most popular Forge module for managing sudo permissions is ssudo, and that's what we'll use here. Here's the hierarchy data listing the users with sudo access. If you're not using Vagrant, you can remove the Ubuntu user from the list. Here's the profile class which reads the data. This allows us to run commands like sudo puppet as a normal user. That's what this part of the manifest does. The sudo conf resource provided by the ssudo module allows us to write arbitrary sudoers config as a string, in this case, setting the secure path variable. The remainder of the profile is concerned with configuring password-less sudo privileges for each user named in the Hira array sudoers. As usual, we get the array from Hira and proceed to iterate over it with each function, creating a sudo conf resource for each named user. Moving on to time zone and clock synchronization, there is a handy Forge module for managing server time zones, Ssh Time Zone. Here's our time zone profile, which uses that module to set all nodes to UTC. We want to make sure that the clocks on all our nodes are synchronized, not only with each other, but with a global time standard as a whole. We will be using the Puppet Labs NTP module for this, and here's the relevant profile. As it happens, there's no special configuration to do for NTP, though you could, if you wanted, specify a list of time servers to contact, for example. Further, let's see Puppet configuration. We need to configure a regular cron job, which pulls any updates from the Git repo and runs Puppet to apply the updated manifest. The profile Puppet class sets this up. There are a fair number of resources in this profile, so let's look at each of them in turn. First, we stop and disable some of the services started by the Puppet package which we won't need. Next follows the cron job which carries out the regular Git updates and Puppet runs. The run Puppet script looks like this. Here's the cron resource which runs the script. The job is set to run every 10 minutes, but you can adjust this if you need to. There's an extra step to run R10k Puppet file install, in case you added any new external modules into the Puppet file, and the addition of the environment switch to Puppet apply. The next resource in Profile Puppet deploys a convenience script named papply, which saves you from having to type the whole Puppet apply command manually. Just running papply from the command line will apply Puppet immediately, without pulling any Git changes. If you want to test Puppet changes from a different environment, for example if you have a staging branch checked out at etc Puppet Labs code environment staging, you can control this with the Puppet env variable, like this. Note that papply passes its command line arguments onto Puppet with $splat, so you can add any arguments supported by the Puppet apply command in this way. We also supply this flag to the Puppet apply command, which will cause Puppet to alert you if any potentially problematic code is encountered, such as referencing a variable which has not yet been defined. If you want Puppet to be really strict, set strict error instead, which will prevent the manifest being applied until all such problems are fixed. Now we'll learn about the Bootstrap process. In order to prepare a new node for Puppet management using the demo repo, we need to do a number of things. The demo repo automates this process, usually known as Bootstrap. Here is the Bootstrap script. It expects to be run with 3 arguments. Puppet repo, the Git URL for the Puppet repo to clone. Hostname, the desired hostname for the node. And branch, the branch of the Puppet repo to use. First, the script sets the specified hostname. Next, it looks at the etc.lsb release file to find out the version of Ubuntu installed. The appropriate Puppet Labs apt repository package is downloaded with wget command and installed. Then the Puppet agent package is installed along with Git. The next step in the Bootstrap process is to clone the Git repo into the place where Puppet expects to find its manifests. Next, we install R10K in Puppet's gem context using the Puppet-specific gem command, and run R10K Puppet file install to install all the required modules listed in the Puppet file. Now we can run Puppet for the first time, which will configure everything else we need. Of course, in order to run this script on the target node, we have to copy it there first. This step is performed by the Puppify script. First, the script sets the URL for the Git repo to clone. You'll need to change this to your own URL when you adapt the demo repo for your own use. Next, we specify the key file used to connect the target node via SSH. Again, modify this to use your own key. After the usage message and processing the command line arguments, the script proceeds to copy the bootstrap.sh file to the target node. The final step is to run the Bootstrap script on the node, passing it to the required command line arguments. That's all about the demo repo.